Hello everybody and welcome to episode 6 of this JavaBot tutorial. Today we're going to talk about two things. First we're going to talk about rendering. You've already seen a bit of rendering. Actually the bots here use it right now and draws a red line towards whatever they're going towards. But we're going to take a bit deeper dive. Actually we're going quite deep because we're going to make our own renderer, which is completely unnecessary but really cool. Secondly, we are going to look at ball prediction. And that's something that's built into the framework and allows us to very precisely predict the ball. And here we're just going to look at the basics, and we're going to make the bot go towards the point where the ball lands, so it will actually be able to predict the ball just a bit. But that's about it for features today. This episode is mostly about learning those features of the framework. Okay, cue the intro. Okay, and let's start up here on the Albert wiki, because in here you can of course find some description of the rendering. And the first one you'll meet here is the Python rendering, and you can see a bit what it's about. Actually there's a GIF here showing a bit what you can do. This might be a bit small, but there's a white line from the car to the ball. There's another red line from the car to the enemy's car, and then there's some text up here. And you should also be able to render some rectangles, but I don't think they're in this GIF. So yeah, this Python code is all great. It shows you a bit about what you can do. However, we are interested in the Java version. And the Java version is actually a bit different. So you can see a bit what it's about here. For Java we have this class called the bot loop renderer, which is the default renderer, and there's only exactly one of those per bot. So to access it, you write this and say, hey, where's my renderer? And you get a renderer, and then you can draw stuff, and it's super easy. And there's not a description of each function in here because it's assumed that your IDE will tell you which functions are available to you. And you should be able to find the draw line 3D and draw line 2D and rectangles and so on. And then you just give it a color and whatever parameters are needed, and you got your rendering. But that's the basic version. Let's dive a bit deeper. Okay, I'm now in the code and I'm in the bot class, and let's get our hands on this rendering. So first let's get our renderer as we saw on the wiki, and let's just draw a line here. Let's choose a nice green, and it's going to be a line from our car's position to the ball position. And there we go, we can now see a green line between the car and the ball. Well, in most cases though, that is exactly the red line as we had before, so there's not really much new to see here. But let me tell you a bit about how this bot loop renderer actually works. When we are rendering something, we are actually making a render packet and sending it to the framework, which sends it into the game and uses the debug rendering of Unreal Engine. And to make such a packet, you have to both start it and finish it. And this is where the bot loop renderer is smart, because this one is prepared right before our bot is called and finished right after our bot is called. Actually, we can go check it out. So it's this function here, the one that takes the GameTick packet. If I press Ctrl B here, we can see exactly where it's called. Okay, so we're now in the bot manager. This is interesting. So this is where our bot is called, and we can see that it gets the renderer for our bot. Okay, and then while it runs, it will do something. It will wait for a packet, and then if we have a new packet, we will start a render packet. Then ask a bot for some controller state. Set the controller state to the DLL, and then finish the render packet. Okay, great. That means our start and finish is automatically called. Let's see what this bot loop renderer otherwise can do. So here press Ctrl B again to see what it is. And we can see that it's something that extends the renderer. And other than that, there's not actually that much functionality in here. we see the map that is used to make sure that each bot has exactly one renderer, and we can see the method to get that renderer, but otherwise it's just a constructor, and then a simple start and finish the packet. So there's not actually any functionality in this class. All of the good stuff is inside renderer. This is where we find the draw line, 2D, 3D, 2D to 3D, there's rectangles, all that stuff. Okay, very interesting. Now the bot loop renderer actually has a brother called the named renderer. This is also a renderer, and this one has a name, so you can group your rendering by name. For instance, if you have some rendering that is for your ball prediction, then you could make a renderer group for ball prediction and only ball prediction. But again, there's not much functionality in here. The only cool thing about this one is that we give them a name, and technically it allows us to send more than one packet because we can just create as many of those as we want. But with that said, there's actually nothing that prevents us from making our own renderer. And that's what we're going to do, because I want a smart renderer and I want to be able to draw something a bit more fancy. We just have to remember to start our packet and finish our packet. So let's make a new class. It's going to be a smart renderer. And this is a renderer with some extended functionality, unlike the others. Let's extend renderer and implement the things that are required, which is just a constructor. But now let's also make the start packet and finish packet that are just identical to our bot loop renderer. We don't have to do something unique here. So I'll copy and paste that. And we just need the previous packet as well. There we go. We can now start adding our own functionality. So what's already implemented is something like draw line, 2D, 3D, there's rectangles and there's strings, but none of these are really good at marking a specific point. So I want to just demonstrate how we could make a simple cross function that draws a cross somewhere. So let's create the draw cross function, and we're going to take some parameters here. We're going to take the color, and here we'll use a color from the Java AWT, and we're going to need the center of the cross, which is just where we draw it, and then we'll have some kind of size for the arms. Okay, so if you take this size and divide it by 2, we know how far we have to go from the center, and let's just call it R. Now we utilize the functions that already exist to draw the lines. Okay, so this would be a line along the x-axis, so we take base in the center, but then we go -r on the x-axis here, but then our end will be +r on the other side. And now we just do the same thing for the other axis. And that should be it. Now we have for the y-axis and z-axis as well. Before we can use our renderer, we have to make the renderer as easily accessible as the bot loop renderer. We can just do this right here in our bot class. So next to our state, for instance, we could have our renderer. And we'll create a new instance here in the constructor. So now, since we always have our bot in our data packet, we also now always have our renderer. And instead of drawing this boring line, let's draw a cross. I of course forgot to make it public, I believe. Let's use the same color of green, and let's use our car position and give it an arm length of 100. We can delete this line, and now before we go any further, there's one thing we have to remember, that is start the packet and finish the packet. However, we cannot put it in the bot manager because this is not our code, this is part of the framework. But essentially we just have to do it right before and after we process our input. So if we go down here, if we just on each side of this one starts our renderer, or starts the packet and finish the packet, then we're good. Like this. And now no, wait, there's one more thing we need to remember, and that is our renderer currently conflicts with the but loop renderer, which means in our move to point state we have to go in here and find the old use of the renderer, and we can delete it, or we can use our own renderer. Yeah, let's do that instead. There we go, that's it. And there we go, as you can see we are now drawing a cross here behind the blue car, but we also still have our red line. So everything works as we expected it. Let's do another one. Another thing that could be funny to draw is a cube. Like if you want to mark a space or something. So let's do that. Just to demonstrate that you can actually do kind of anything in here. Even if you make a custom class for something, you could also define a way to render that one. So our draw cube is going to have a very similar signature. We again have a color and the center of the cube and the size of the cube. And again we defined an R to be our size divided by 2. And this time we are going to need a few more lines, because a cube consists of, what is it, 4 plus 4 plus 4 lines. So yeah, we're going to need 12 different lines that are offset in different directions. But don't worry, I'll make a cut here. Okay, there we go, that's all the lines that we need. So you just have to follow the same pattern. Maybe that's easier said than done, but notice here that up here all the sets are negative, and all over here all the sets are positive, and then it's just all combinations of the others in here. Down here it's all the y's that are negative and then positive, and here it's x that are negative and then positive, and all the other combinations. And let's try and see how this one looks. So in our base but we can just change this one to draw cube. And see, now we have a tiny little cube. Oh, that's adorable. Yeah, so now I showed you how you can do this, and it's really only for your own sake. It's just a tool, it doesn't add functionality to your butt, but it might be easier to debug if you have some more advanced rendering. And as I said before, you can extend this as much as you want, so feel free to do whatever you like. So the next thing we're going to talk about is the ball prediction. And actually there's already a class in the folder called ball prediction helper. And here we find a function to render the prediction. And now that we just set up a renderer, let's see if we can draw the ball prediction with our own renderer. So what this function needs is a ball prediction, then how many game seconds we want to draw, and then the color and our renderer. Easy, let's do that. So the first thing we need is our ball prediction, and we can get our ball prediction by typing albert_dll.getBallPrediction. This function can, however, throw an exception, which we have to catch. So we will surround with a try and catch, and we should be good. Let's just move our ball prediction helper call in here. Now let's say what is returned by this function and pass it to our helper function. Next we need the game seconds that we want to draw to, and the ball prediction is able to look forward in time 6 seconds. So what we're going to do is we're going to type data.time plus 6. Then we have to choose a color. Let's choose the same green, and then give it a renderer. And lastly, we just have to cast this to a float. Let's try and run this. So, as you can see, we are now drawing where we predict the ball is going to be. And it's a green line right here. And you can see how it will bounce and all that. The renderer doesn't update while we count down, but that's okay. Now we can see it's rolling and it's bouncing, and if one of these butts would shoot it up the wall, we can also see that it actually has... Well, okay. Own goal, that's... So here I'm finally able to show off how the ball actually bounces. And you can see it's pretty exact. I don't think you can make something that's better than this. And yeah, we're going to take use of this. It's calculated by the framework, which means it's available to all the bots already and doesn't cost us anything. I've gone ahead and found the ball prediction wiki page, and as you can see, again, it's very sparse, but in reality it's also very simple. You call the get ball prediction, as I already showed you, and this is essentially just an array of slices, and each slice contains some information about the ball's physics at that point in time. There are 6 seconds worth of slices at a rate of 60 per second, so that's 360 in total. And you can see here how it accesses a slice, gets the physics, gets the location, and it just draws that location here in the example. Iterating through the slices is actually a bit computationally heavy, so don't do it too often. And if we click here, we can see the general wiki's description. Here you can see a bit about how it was made. It was made by Chip, and you can see the model here on this link. And as the note here says, it's an estimate, it's not exact, because the game is not completely deterministic. But it's very close. Before we get started with the ball prediction, let's just take this function and move it to a renderer, because that's why we made it, so we can render special stuff like this. So now we don't need the renderer as a parameter, and also this ball prediction, we could actually just fetch it right here. So we'll make the call to the albert.dll get ball prediction right here, and we'll surround it with a try and catch. And for some reason it plays this one out here. Let's just put it back in here and remove this. Renderer, well, now we have our own renderer, so we can just do it directly from here. It's now telling us to remove static, that makes sense. Okay, I just want to make one more change, and that is, instead of taking game seconds as a parameter, let's just take the duration that we want to render into the future. So delete this, and let's make a double that is duration, so we don't have to cast. Now we'll calculate at which slice we're going to stop. So since we know there's 60 per second, we can actually calculate exactly what this I is going to be at the time we need to break. So simply we're going to stop at 60 times R duration. And this condition can then be when I is greater than stop. Well, stop. Cool, let's rename it to draw ball prediction. That makes a bit more sense now. And we can just confirm that it works by going to our bot again. And we replace this with our new function. Let's choose a nice pink this time so we can see that it's actually different. Not gonna lie, I'm a bit disappointed by the pink, but sure, it worked. Okay, we are now ready to actually use the ball prediction. We've seen a bit about how it works, but now let's actually use it. We are going to make a function that can tell us when the ball is reachable. So just the next reachable spot. And it's going to be very simple here in the start. Like, our bot is very stupid, so let's not try to pretend that it can aerial and all that stuff. Let's just make it super simple. And then as we improve our bot, we can go back to this function and improve it. Currently our bot really only works at ground level, so let's find the first spot where the ball is at the ground. So it's going to be a public static function. We'll call it next reachable, and it needs our data packet, so we can access all the interesting stuff about our bot and the ball. Let's start by getting the ball prediction. Now we need to iterate through the slices, and we'll just do a very naive linear iteration. We don't have to check every slice because there's not a big difference between them when there's only passing 1/60th of a second. So let's iterate like every 6 or something. A simple for loop. Our end condition is when we passed all of our 6 seconds of 60 slices per second, and we increase by 6 every time. This is how we get our ith slice. And let's extract the position in this slice to our own vector 3. We can also calculate how far into the future this is just based on I. And now we can start assessing whether we can reach this position in this time. First, let's check the z coordinate of the position. If the ball is in the air, we can't reach it anyway. So the ball's radius is 92 approximately, and our car's height is somewhere around 24. So I picked a number that's just 100 straight. That should be fine. If it's below 100 on the z coordinate, we should be able to touch it. And in the case that it's above, then skip this slice. So now let's consider, can we reach this spot in that amount of time? So we're going to check our speed, like how fast are we actually going towards this point, and that'll tell us a bit about if we can get there in time. And then of course we need the distance. So we'll start by finding a vector that goes from our car to the ball. That's the ball position minus our car's position. We'll also find a normalized version of this because we're going to need it. And the distance is simply the magnitude of this car to ball vector. We're going to need this car to ball direction to assess how fast we're actually going in that particular direction. And that's again our dear old friend, the dot product. So this gives us our current speed in that direction. This might not be the maximum speed, and if it's not the maximum speed, then we can expect to accelerate. And since we don't have an accurate model of the acceleration right now, we'll just do something very simple. Let's take the average of our current speed and our maximum speed and say that's probably the speed we can reach it at. So our maximum speed is 2300. You can find values like top speed and other kinds of things on the wiki if you need them. Also, if you think this is very oversimplified, well then I encourage you to improve this. This tutorial will just show you a good start, and you are basically meant to go in and improve all of these kinds of things. Now we have our distance and our expected speed, so we can now find the travel time. And we can compare our travel time to the time that this slice is in the future and say, if our travel time is less than that, then we can reach it, and let's return this position. Wait, actually we're going to need some more than just the position. We're also going to need the time. Let's make a small class to hold these values. We will call it prediction data. It'll contain a position and a time. And using the magic of IntelliJ, we have a class quick and easy. And here we are now returning our position and our time. Now in the case that we cannot reach the ball at all, or in the case where this function fails, we need to define what we do instead. And we could return null, but I don't want to create null pointer errors. So let's create a prediction data that contains the current position and a time of 0. Nice. Let's go ahead and make our at-best state use this prediction. So instead of choosing the target and the target speed like this, we are now going to call our prediction helper instead and found out where can we reach this ball. So now we set our target equal to the predicted position, and we set our target speed equal to that distance divided by the time, and that's our speed. Finally, let's draw this position because we have a smart renderer now. We'll draw across where this target now is. And look at that, it'll now predict where it can hit the ball, and hopefully will also correct the speed. Yeah, there we go, see how it goes slow. Our bot is actually finally a little bit intelligent. And it can almost dribble the ball, as you see. Nice. Another important step has been made. Actually, let's finish this episode off by offsetting that position just a tiny bit. So we are more likely to hit it towards the enemy's side than our own side. And now, well, that will give us a little bit of strategy as well. I'll start by creating a little helper class called goal that will tell us where the goals are. The goal class will just contain this very simple little function where we can get the goal of any team. If team is 0, we'll return the blue goal, which is at this position. And if it's not, then we will return the orange goal at this position. And back in our add state, we want to calculate this small offset and add it to the position. The offset direction will be the same as the direction from the goal to the ball. And then we scale it by some small number, like 50, because then it's still inside the ball, but it's now on the opposite side of the ball. And hopefully that will push it towards the goal. Oh yeah, and this small trick right here will invert our team. So if we are on team 1, then this will be 0, and if we are on team 0, this will be 1. That's just a smart thing to know about, so there you go. But let's go ahead and try this out. And you can see the crosses are now slightly offset. And the blue one is going to a point on the blue side, and the orange one is going to one on the orange side. So hooray! We now have some very basic strategy. Orange is about to own goal anyway. Oh, he saved it. Nice. But yeah, thank you for watching. That's it for this episode. See you another time. Have fun.